first things first. You're looking at a simple question. You guys have seen this before. In the back of your heads, what is 3 squared? 9. Hey, beautiful. How'd you get that?
3 times 3.
You multiplied 3 times 3. Got it. Good stuff. How about now? 4x squared. 16x squared.
Distribute the exponent to both variables.
Okay, so there's a couple ways we could look at this. One is 4x times 4x, square it. 4 times 4 is 16, x times x is x squared. The other thing is, when we have parentheses raised to a power, we can distribute the exponent. So it applies to the 4 and also to the x. So 4 squared 16, x squared is 6. Good stuff. Let's make it a little bit more complicated. In the next slide, you're given something and it's squared as usual. And I don't want you guys to do this just yet, but please take a look at the choices as well as what is being squared and think about something that you might notice. 30 seconds, observe. What do you notice?
Oh, wow.
All right, if we could, maybe just 15 seconds, turn to somebody and share something that you noticed. Ready, set, go.
The title of binomial theorem.
All right, let's hear a few of them out. What do you notice? Popcorn them. 2 exponents. Got it. What else? Minuses. What else? Multiple variables. What else? Things are squared. Good. What else? Ah, good. FOIL coming up. What else? Subtraction. Yes, absolutely. Cool. What about these answers? What types of answers are they? Addition and subtraction. A and C, what would you call those 2 things? Versus B and D. Trinomial versus binomial. For those of you that remember your Algebra 1, the correct multiplication of this expression, how many terms must it have? 3. Remember that binomial multiplication often necessitates a middle term. So let's actually do this one really quickly. I heard a couple people say it. How do we multiply this out? FOIL. Thank you guys. I'm going to take this away and I'm going to multiply 4x minus 2y. First terms, 4x times 4x. 16x squared. 4x times negative 2y. Negative 8xy. Inner terms, minus another 8xy. Last terms, plus 4y squared. One last step, what is it? We're going to combine the middle terms, or if they were opposites, we would cancel them. But here they create a middle term, negative 16xy plus 4y squared. So there's a process. It's not as simple as just distributing the exponent. We actually multiply it out. We combine like terms. And binomials, when we square them, can have trinomial products. Okay, questions on this one? Question, go ahead.
Can have or will have?
Can have. There are times when the middle term cancels out. Okay. Going once, going twice. I got a buyer. We have one more degree that we're going to escalate this. So on the next slide, what's different? We have a binomial cubed instead of a binomial squared. When we squared it, the binomial became a trinomial. When we cube it, just out of curiosity, any thoughts about what might happen here?
There's 4.
Well, you might end up with 4 terms. If I were going to multiply this out by hand, how might I go about doing that?
You just
FOIL, first, outer, inner, last. That's probably not a bad idea. So I would write this out, 4x minus 2y times 4x minus 2y times 4x minus 2y. Only the problem here is that I've got first, and then this binomial is first, and then these guys are outer, so what about these? And FOIL all of a sudden sort of collapses into ambiguity. There is still an approach here. What's one thing we could do?
We can split it into two sections.
We could break this into 2 problems. Like I could multiply these ones out, right? And this would be a trinomial, the same one we just got, 16x squared, is that right? Minus 16xy plus 4y squared, and then multiply that by 4x minus 2y. Now we can multiply a trinomial times a binomial. We could use an area model, we could use distribution, sorry, this should be xy. Distribution, we could do a lot of things here, but if you guys are like me, we're already taking up a bunch of space, we're now just still working on the same problem, and now I have to do 6 more multiplications and deal with all sorts of expansion. It starts to get to be a lot of work fast. And then, not actually going to do this, but would like you guys just to imagine that I changed this to an 8 all of a sudden. If that were to the 8th power, now we have to multiply 8 different binomials over and over again, and all of a sudden this becomes an insurmountable task, which is why we have a theorem to help us with it. Okay, I'm going to switch the screen to something that is going to be significant. You guys have seen it before. Okay, next thing that I would like to discuss is this theorem right here, the binomial theorem, the binomial expansion theorem. You guys have seen this a couple of times, and it is definitely not pretty. There's a lot of stuff in there. There's one point where it just sort of trails off and the formula disappears for a while, and you're not sure what to do with it. I think that once you guys see this done, you'll be able to repeat the process and even have a better inclination of where it came from. So we're going to do an example. We are going to do 3x plus 2 to the 5th power, and we're going to expand this. So the first piece of advice that I'd like to give you on these is to be very, very clear about what is what. So as I'm looking at this, my original problem, and comparing it to the formula, I'd like to label some variables. So the thing outside, the n, that's 5. So I'm going to go here and label 5 as n. That way I don't forget about it. Then inside, we've got a plus b. The first thing, that's 3x. That must be a. And the second thing, that's 2. That must be b. So I've identified my variables, a, b, and n. And then I'm just going to start writing out every piece of this formula, substituting in everything that I possibly can. So starting in the very beginning, including the probability notation for combination, n is not n, n is 5. So this is 5, choose 0. It's not a, it's 3x. So 3x to the, it's not n, it's 5, 5th power, times b, which is not b, it's 2, to the 0 power, like that. And that is the first term in our expanded response. And you'll see how this works out in just a second. But now we're going to continue on to the next term, which is NC1. Okay, n is still 5. C is still C, 1 is still 1. A is still 3x, but notice what happens to the exponent here. It goes from being n to being n minus 1. And n was 5, so n minus 1 would be 4. So it went from being 5, the variable on 3x, I'm sorry, the exponent on 3x, to being 4, the exponent on 3x. Next, b is 2, and the power here is 1. Okay, so I want you guys to observe a couple of patterns. Brian, thought.
Just keep going down all the way until it's 1.
Exactly. So you're seeing some things here, right? Like 0 became 1, it's about to become 2, and then 3, and then 4, and then 5. 5 became 4, it's about to become 3, and then 2, and then 1, and then 0. And 0, 1, 2, 3, 4, 5, it's going to follow a linear pattern. Yes?
Are you able to think of this as like an upgraded combination? Because you're still trying to find out, since combination is like you start with the number, exclamation mark, you go 5 times 4 times 3 times 1. This is kind of the same thing, but this is like a theorem based.
It's very closely related to that, and we're actually going to be using that in just a second. But yes,
You think of that.
you can think of it in that similar terms. Yes.
So are we trying to get the existing zeros to 5?
Yes.
The existing zeros?
Yeah.
You mean like here or here?
Yeah.
I'm sorry, what do you mean by the existing?
Keep writing it until you get that 0 to 5, and then the 0 there to
Yes,
5.
the exponent zeros are the same.
Right, so that's exactly what we're going to be doing, is we're going to keep going until these exponents have switched places. So let me just power through that really quick. So plus 5c2, that one goes up, 3x to the third power, 2 to the second power. Continuing, plus 5c3, 3x to the 2 power, 2 to the 3 power, plus 5c4, 3x to the 1 power, 2 to the 4 power, and then plus 5c5, 3x to the 0 power, 2 to the 5th power, like that. All right. I know that this still is a lot of material, there's still a lot of things here. But the beautiful news here is that this is now just a substitution problem. There's no multiplication, well there's multiplication, but not like foiling and binomials times trinomials and things like that. It's just substitution. So we'll start with doing a little of it. 5c0. This is something that we can simplify into a numerical value. So remember what you guys learned earlier in the unit, 5c0. Is this 5 factorial over 5 minus 0 factorial times 0 factorial, right? That's the way the combination formula worked. And so as we draw this out, 5 factorial is 5 times 4 times 3 times 2 times 1. 5 minus 0, 5 times 4 times 3 times 2 times 1. And then just as a quick review, 0 factorial, what is it? Be so careful. 0 factorial, yeah, this is something that you might have grazed over in your textbook, but 0 factorial is defined as 1. And the reason that we have to do that is because if we made this 0, the entire denominator would be 0, then we'd have 0 in the denominator, which would be illegal, undefined. We're not allowed to do that in math. So 0 factorial, we just define as being 1. So I'll even put an extra 1 down there for us. 5, 4, 3, 2, and 1 cancel. 5, 4, 3, 2, and 1 cancel. What's left over?
1.
1 and 1. So what is 5c0? 1. So here, I'm just going to replace it with a 1. Times 3x to the 5th, which is in parentheses, and 2 to the 0 power is 1. So 1 times 3x to the 5th times 1. plus, and continuing on and on down the line. This is a mechanical process at this point. So for the sake of this video not taking forever, I would like to just emphasize that what we're going to do next is to repeat the same process. For each combination, we're going to use the formula. For every exponent that we can simplify, we're going to simplify it. And when it's all said and done, we're going to have a 1, 2, 3, 4, 5, 6 nomial as our response. Okay. Question, go ahead.
So, what do you mean by, I don't correctly, because I was gonna ask, would the ones then be 5s and the 3x to the 5th, would that then be 3x?
You mean here?
0?
Let's actually simplify it out. So what we have to do is we have to distribute the exponent. So the ones, they're just ninjas, so they're going to disappear. But what we are going to have here is 3 to the 5th power, which I don't know off the top of my head. Oh, thank you. 243? So this is 3 to the 5th, x to the 5th, and 3 to the 5th is 243, x to the 5th. That is the first term here. Cool? All right, let's do one more just so we can see this through. So we need now to do 5c1, which is going to be 5 factorial over 5 minus 1 factorial times 1 factorial. A lot of exclamation points in here, aren't there? Okay, 5 factorial. 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. 4, 3, 2, 1 cancel. What am I left with? 5. So 5c1 is going to be 5 different ways we could do that. So here I'll substitute it in. 5 times 3 to the 4th, x to the 4th, times 2. Okay, 3 to the 4th, what is it?
81.
81. What's 81 times 5?
400 something, and then it's gonna be.
And then you're going to multiply that by 2. So
810.
So hang on, this is going to be 5 times 81 times x to the 4th times 2. And the next thing we're going to do is 5 times 81 times 2. Help me out, guys. What is it?
810. 810 x to the
810 x to the 4th. And look at what's starting to shape up here. 243x to the 5th, 810x to the 4th. This is starting to happen. Go through it 4 more times, and you'll end up with a beautiful polynomial. And even though it is quite a bit of work, it still beats the heck out of foiling something 5 times over. Miko and then Noah. Go ahead,
For
Miko.
all the C's, can we just plug it into our calculator?
All the C's? So like these expressions right here.
Yeah.
You can plug it into your calculator, absolutely. There's also another way we can do that, and we'll talk about it in a second. But Noah, you had a question too.
For the test, quiz, and or final, how many of these questions are we going to have?
That's the whole chapter.
None.
So you will see these. I don't know the exact number that you will see, but you can also breathe a sigh of relief. We know how much can go wrong in one of these. We know that there's lots of places for tiny calculation errors. So if your response isn't perfect, that will still be okay as long as your process is consistent with what it should be. Okay, go ahead. Yes.
Will you provide us with this equation or no? We have to go
With
right
the
into it.
formula?
Yeah.
Yeah, we're gonna give you this.
Okay.
Yeah. Yeah, we're gonna give you that. Nathan.
There's a separate problem that's like, let's say the problem is like 5C, like 2 or whatever the number is. Can we just like use the calculator to like put it in and we just write down that? So it's only that's show work for
You can use a calculator on these things if you have a calculator that will do it, but there's also this formula down here that you're going to be tested on elsewhere in the test. And even though this is easier, you should still understand what's going on with factorials and how we get those values. Go ahead.
So expanding is one thing, but also simplifying it. So remember how we went over a problem that had a negative b? Well, we have to
Okay.
simplify that because that's kind of.
No, we're going to try and keep it pretty straightforward here, especially if you're doing this part by hand.
Alright.
It's a lot of work, and we're still getting to a point where it's useful. So right now it's just a skill, we're getting through it, but we need to acquire some use for it. All right, so questions on that part? All right, I need to change something here. Guys, I apologize if this gets all out of whack. It's about to. Okay. I want to talk about the instructions for this problem right here, number 62. Okay. So please take a look at these instructions right here, where it says use the given value of n to find the coefficient of x to the n in the expansion of the binomial. And so here, this is the problem we just did. And one way to go about doing this problem would be to expand the binomial and then actually figure out what the coefficient is. Go ahead.
If n is 3, then what is 5 become? Where is 5 go?
Okay, so you're worried that 5 is now also an n right here. Yeah, and that's totally confusing way of asking this problem. But I wish they'd use a different variable here. Like, can we please just call this maybe m instead of n, just so that we can be more clear about this? So here's the original problem. 5th power. We're working on expanding it, but it's a lot of work. And this question asks us to find the coefficient of x to the n, meaning that when the power of x is 3. We want to know the coefficient of it. So to give you an idea of what they're talking about, in the final expansion, when x has the 5th power, its coefficient is 243. When x has the 4th power, its coefficient is 810. This wants to know what is the number in front of x when the power on x is 3. So really, this is a confusing way of asking it, but it's asking you to tell me the coefficient of the 3rd term in the binomial expansion of this, which is to the 5th power. Okay, crazy stuff, right? Just so we can check our work, can we do the next one real fast? So we know what it's gonna look like? Okay, so 5C2. And I know I'm all over the place here, guys. It's a ton of space. Give yourself extra paper here. 5 factorial over 5 minus 2 factorial times 2 factorial. This is 5, 4, 3, 2, 1. This is 3, 2, 1 times 2 times 1. Any objections to where I'm getting this? Cool. 3, 2, 1, 3, 2, 1. 5 times 4 is 20. 2 times 1 is 2. Magic number is 10. Still with me? Great. So 10 times 3 cubed is 27, x to the 3rd, and 2 squared is 4. So in order to get the coefficient of x cubed, I need to multiply 3 things. This 4, this 27, and this 10. Help me on a calculator.
1080.
1080. So this is going to be 1080 x to the 3rd, which is exactly what the question is asking us for. So they want to know the coefficient of the binomial. The coefficient is 1080. So your answer for this problem should be 1080. Put a circle around it, put a star next to it, and walk away. But what I want to talk to you guys about is actually a quicker way to identify this. And we're going to use a Pascal's triangle in order to do it. Okay. Actually, does anybody have one of those triangles handy?
I do.
Thank you so much. Guess I should have gotten that out. Oh, you're the best. Thank you so much, Kaylee. Okay. Can I fold it? Is that okay? My apologies. I'm folding up your entire triangle here. All right. So, Pascal's triangle. Oh, I know. I know exactly how you feel, man. Okay. The original problem is a 5th degree expansion, and we are looking for the 3rd coefficient. We want row 5, item 3. But in the video, remember that they pointed out the very top row does not count. Neither does the very first column. So watch what I do here. I want row 5, step 3. Skip the first one. Here's 1, 2, 3, 4, 5. I'm going to scoot that up a little bit so I'm not hiding behind my work here. Okay. Skip the first. 1, 2, 3, 4, 5. Skip the 1. 1, 2, 3. Look familiar? Look familiar? It's the 10. So the magic number is 10, which, remember, I had to multiply by 27 and also by 4. That's where the 1080 came from. Questions on that? You guys want to try one on a shortcut like this? See if we can do this?
Miko, yeah.
Yes, Miko.
So, for the final answer for number 62, it would be 1,080.
Would just be 1008, yes. Okay, so the 10 is a critical piece of that, but we saved ourselves from having to do this. And I'm actually thinking we might be able to make this even faster if we do another. Can I erase this expansion?
Yeah.
Okay. Ton of stuff. And then we even have another fun problem next. But this next one is even more fun than this, I promise. Okay. Let's take a different problem here. So what about like number 59? Or you know what? Can we do better? Let's do 63. What are some of the critical numbers in 63? There's a 12. There's this 7. We care about that.
That's pretty much it.
And that's pretty much it. Okay, so let's look at the triangle. Which row do I want?
Well, 7th row.
So 12 down, 7 in, right?
Yeah.
Skip the first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Skip the first. 1, 2, 3, 4, 5, 6, 7. 792. Let's see where I'm at. Okay, so the magic number here, I'm just going to write it down, is 792. Is that the coefficient?
No.
What did we still need to multiply by?
5, 2, and 5.
Yeah, there's some other things, right? And it wasn't exactly 2 and 5.
Oh, no, I do combination.
Right. And remember, we want the x power to be x to the 7. Okay? So that means that what's actually going on here is that we are going to have somewhere hidden in there 2x to the 7th power. And then my other piece was 5. And so if this is 7, what's the other exponent? You guys remember how the pattern worked? It was like
7.
5, 0, then 4, 1, then 3, 2.
6. Wait,
5,
5.
right? Because it has to add up to 12. Okay? So 2x to the 7th and 5 to the 5th, meaning that the numbers that we need to multiply by here are 2 to the 7th and 5 to the 5th. It's going to be gigantic. Calculators. 792 times 2 to the 7th times 5 to the 5th.
Oh my god, what is this number?
Scientific notation. 2 to the 7th, 128.
3.162.
5 to the 5th, 792. What do we say? 2 to the 7th is 128, and 5 to the 5th is 3125. So 792 times 128 times 3125. How many zeros is that? It's 3168 and then 5 zeros. Am I counting that right?
Is there a cutter?
So boom, boom, 316,800,000.
Mr. Henner, the
Yes.
combination should be 6, 12, and 6, not 12 and 5.
Combination should be 12 and 6.
Because it's gonna be the exponent we want minus 1, because it goes from 0 to that number, so it will be minus 1, so 0, 1, 2, 3, 4, 5, 6.
Okay,
So,
but are we going up to 12? Isn't that the power?
yeah, but like,
And 7 and 5 is 12, right?
yeah, but like it still goes from 0, because that one is, the original one will be 12C0,
12C0.
and then,
Oh, I see, so it goes all the way down to 0C12, and so then
it will
there's
be-
13 different things,
yeah. So it'll
not
be
12 different things. Okay, cool. So then what does that change about this?
It turns it into
5 to the 6th?
Yeah, 12 to the 6th.
12 to the 6th?
It's
5 to the
924.
Right?
Oh yeah, that one is also
This is a 6.
Yeah, that's also
Which means
6.
this is now,
really big.
yeah, what is 5 to the 6th?
Was
I see, thank you for that.
15,625.
15,625?
Yeah.
Okay,
And
awesome.
the combination's also different.
And it's gonna change the combinations?
Yeah.
Okay, but here wait, it won't change what we choose out of this, right?
No.
Okay, cool. But then this is still gonna be the coefficient. Cool. So don't stress then the combinations, but in terms of the coefficient, if you're looking to use the Pascal's triangle shortcut, just recall that it should add up to one more?
No, 12,
Yeah,
it should
it's
be
one more.
2 to the 6, right?
It's
No,
924.
No, I'm
No.
still concerned because,
no.
so, yeah, so, I didn't know the color. Where did I put my blue marker? Okay, so what this is gonna look like is the highest possible exponent is gonna be x to the 12th. So it's gonna be something that's like some number times 2x to the 12th times 2 to the 0, right? And then the next term is gonna be some number times 2x to the 11th times 2 to the 1. And then plus some number that's 2x to the 10, 2 to the 2. And we're gonna keep going like this, right? To x to the 9, 2 to the 3, x to the 8, 2 to the 4, x to the 7, 2 to the 5. Right? And isn't this the 1, 2, 3, 4, 5, 6th term? The power on it is 7, which is what we're looking for. And the corresponding power on the B piece is 5, so it does add up to 12. Is that right? Like there's, I think that it should, because that's the pattern, right? Is that it always adds up to whatever the highest exponent is. Good stuff.
Want to fix that for the,
I'm sorry?
want to fix that exponent now?
Okay,
Back to
so
5
let's
to
go
the
back
5th.
and switch things back to where they were a second ago. Okay, so then this should be, I'm using the wrong color now, 5 to the 5. Still here, and then whatever that was. Cool. Questions on this one? Alrighty. I had another problem for you guys, but I am concerned about time because that took about twice as long as I was expecting it to. Mrs. Hastings, will you stop the video?